Welcome to this deep dive. Today, our mission is to unpack a highly specific, honestly kind of maddening developer's log from May 26th, 2026.
Yeah, it was written by a software engineer named Ang. The log is titled Notes on Go Programming, Part 06, How Go Manages Its Own Toolchain.
Right. And we are diving into this because, well, whether you are managing, these massive microservice architectures or you're just fascinated by the clever system design, you've definitely wrestled with it.
Oh, absolutely. The universal headache of version management.
Exactly. We've all been there. And this log outlines this incredibly stubborn local environment bug that ultimately reveals a total masterclass in modern software architecture.
It really does. Ang's notes document this scenario that completely challenges the basic assumptions we make about how operating systems, execute software.
Yeah.
It starts out as this hyper-localized troubleshooting session, but it quickly expands into this blueprint for how programming languages are basically evolving to manage themselves.
Right. Completely independent of the underlying OS, which is wild. Okay, let's unpack this. To understand the gravity of the technical dilemma Ang ran into, I want you to imagine something.
Okay, I'm ready.
Imagine you buy a brand new, top-of-the-line 2026 sports car. You sit in the driver's seat, you turn the key, and the digital dashboard lights up, right?
Yeah, standard new car experience.
But the screen insists you were driving a 2025 model.
Oh, that would be frustrating.
Right. So you swap out the computer system, you get new keys, you literally physically verify the VIN. But no matter what components you replace, the car is absolutely convinced it's a year older than it actually is.
That dissonance right there, that gap between physical reality and system output, that is exactly what Ang experienced on an Ubuntu 26.04 machine.
It's just so baffling.
It is. Ang was working on a pet Go project, currently pinned to version 1.23.x, and decided to upgrade the local environment to 1.25.x.
Or, I think, ideally, the bleeding edge 1.26.x, right?
Yeah, exactly. And, it should have been a standard operation, just a totally routine upgrade.
Right? And Ang threw, every standard deployment method at this thing. The log details installing and uninstalling, using DEB packages, unpacking raw tar files into the user local Go directory.
And eventually even leveraging Mize, right?
Yeah, Mize, which, if you don't know, is this really robust Rust-based environment management tool. It's literally designed specifically to handle these kinds of versioning swaps.
Yeah, it's usually rock solid for this.
But every single time, Ang would open the terminal, run the command Go version, and the output was stubbornly frozen at Go 1.25.0.
The persistence across all those different installation methods, that's the first major clue.
How so?
Well, when Mize or similar tools like DNS manage versions, they rely on shell shims.
Right, the shims.
Yeah, they manipulate your path environment variable so that when you type Go, the operating system hits their shim first. Then that shim routes to the correct binary based on your directory.
Got it. So if the shim is failing, you'd usually just assume, okay, the path is misconfigured.
Exactly. You'd check your bash arc or scite, fix the path.
But, and this is where I got so stuck reading this, Ang eliminated the shell shims entirely.
Yeah, this is the part of the log where the behavior crosses from just a simple configuration error into a fundamental OS anomaly.
Right, because Ang completely bypassed the symlinks, bypassed the path variables, and executed the absolute path of the newly installed binary directly.
Yep, ran user lib go 1.26 bin go version.
And the terminal still returned Go 1.25.0. I mean, wait, how does that even happen? If I pass an absolute path to the exec system call in a Unix environment, pointing directly at a binary named 1.26.
The operating system loads that exact binary into memory.
Exactly. The OS doesn't lie about what it's running. How can a file with 1.26, literally right there in its name, lie to you like that?
What's fascinating here is that the operating system isn't lying.
It's not.
No, the exec.syscall did exactly what it was told. It loaded the 1.26 binary into memory and executed it.
Okay, then why the 1.25 output?
Well, for that binary to then output 1.25.2, it means the Go 1.26 executable contains internal logic that actively intercepts its own execution flow.
Whoa, so it's questioning itself.
Yeah, it queries its environment, and it intentionally overrides its own identity. It is deliberately proxying the command to a completely different version of itself.
That is wild. That implies the executable we think of as just a compiler is no longer just a compiler, it's acting as the dynamic router.
Precisely. It's a router. And Ang actually found the routing table by digging into the GOENV settings.
Right, looking at the configuration file at the home config go NV path.
Yeah, and there was this smoking gun, a single dormant environment variable dictating this entire weird behavior.
Go toolchain equals go 1.25.0 plus auto.
That one variable is the crux of Go's entire self-management architecture.
Okay, break that down for me because the syntax seems super specific.
It is. To understand its power, we have to look at that syntax. If the variable had simply been go toolchain equals go 1.25.0, it would just act as a hard override.
Like forcing the system to behave as version 1.25.0 no matter what.
Exactly, regardless of context. But that little plus auto suffix, that introduces a really sophisticated layer of conditional logic.
Right, and Aang tested that logic, right, by changing the variable to go 1.24.0.
Yeah. And instead of throwing a, binary not found error or something, the terminal immediately printed this message.
Go : downloading go 1.24.0 Linux AMD64. It just went out to the internet and grabbed it.
Instantly. And that terminal output exposes the really deep separation between what they call the host Go and the active toolchain.
Okay, host Go versus active toolchain, what's the difference?
So the host Go is the binary actually installed on the operating system. In Aang's case, it's that 1.26 binary installed via mize.
The one sitting in the user lib folder.
Right. When you invoke a command, this host Go wakes up, but it actually halts before any compilation occurs.
Oh, so it pauses.
Yeah, it enters a bootstrapping phase where it parses the go.mod file in your current project directory to read the Go directive.
Okay, so let me make sure I have this. It scans the project's source code, sees a line that says, go 1.26.3, and then it compares that requirement against the Go toolchain variable.
Precisely. It's checking its instructions.
Oh.
And if the project requires 1.26.3, but the host Go binary determines it can't fulfill that requirement based on those Go toolchain rules, it doesn't just fail and throw an error.
It dynamically provisions the required environment.
Yes. It reaches out to the Go module proxy, downloads the exact toolchain required, the compiler, the linker, the standard library.
And it caches it locally in the geopath pkg mod directory, right?
Exactly. Then, using os.exec, it seamlessly passes all your command line arguments to that newly downloaded binary.
That completely flips the traditional model on its head. I mean, we are so used to the operating system managing the software.
Right, through package managers and paths.
But here, the installed binary is basically acting like a middle manager.
Oh, that's a good way to look at it.
Yeah, like you handed a blueprint,
Right.
the go.mod file. The manager looks at it, realizes the factory doesn't have the specific robotic arm needed for this blueprint.
So it just goes and gets it.
Exactly. Without bothering you, the manager orders the arm, installs it on the assembly line, and manufactures the part. You just hit build, and the language runtime handles its own entire supply chain.
If we connect this to the bigger picture, this architectural shift from a system-managed model to a project-managed model, it fundamentally changes team synchronization.
Oh, totally.
I mean, for decades, the industry has relied on external shell-level tools, right? Like NVM for Node, PyM for Python, or ASDF to manage these environments.
And those tools are inherently fragile. They rely on shell hooks that, honestly, they break all the time.
All the time.
Like when you switch from a terminal to an IDE or when you run automated background scripts, you end up with a project that compiles perfectly fine in your terminal, but completely fails in your editor.
Because the editor isn't sourcing the shell shim correctly. Exactly. And that reliance on shell-level interception, it creates the classic works on my machine syndrome.
The absolute bane of every developer's existence.
Right. Think about it. A developer might upgrade their system-level Go version just to test a new feature, forget to downgrade it, and suddenly they commit code that relies on a newer standard library.
And then they just break the build for everyone else on the team.
Exactly. But by pulling the version resolution natively into the Go binary itself, the project repository becomes the absolute source of truth.
So what does this all mean? It means the go.mod file enforces deterministic environments across the entire engineering organization.
Yes, no matter where it's running.
Right. If the repository dictates version 1.26.3, the project will automatically compile using 1.26.3 on the senior engineer's laptop, on the new hire's machine on day one, and on the remote CI/CD build servers.
Seamlessly. The host Go acts purely as a vessel to read that requirement and execute it. It guarantees immutability in the development lifecycle.
Which saves teams so much time and money. No more juggling versions across different projects. Go just handles itself.
It really does. But bypassing those external tools and managing the toolchain natively, it actually solves a much more dangerous structural IT problem too.
Which is?
It's the requirement of root access.
Oh, right. But wait, here's where I get a little hung up. Passing the execution flow to a dynamically downloaded binary introduces a massive theoretical risk, doesn't it?
How do you mean?
Well, if my code is automatically downloading an executable from the internet and just running it locally, how is that not a giant remote code execution vulnerability? It sounds like a security team's worst nightmare.
It totally would be if it weren't for the cryptography underpinning the module proxy.
Okay, explain that.
When the host Go downloads a new toolchain, it doesn't just blindly trust the payload. It queries some .golang.org.
Which is an append-only cryptographic transparency log, right?
Yes. It retrieves the expected SHA-256 hash for that specific toolchain version.
Ah, the checksum database. Here's where it gets really interesting. So it's mathematically verifying the fingerprint of the compiler before it even allows it to execute.
Exactly. The host Go calculates the hash of the downloaded payload locally, and then it compares it against the transparency log.
And if they don't match?
If even a single byte has been altered, say by a man-in-the-middle attack or a compromised mirror, the hash won't match and the execution halts immediately.
Wow.
And because this transparency log is built on a Merkle tree structure, it is practically impossible for an attacker to tamper with the historical records without detection.
That is seriously robust. Yeah. And that supply chain security is what allows Go to safely pull this entire process into user space.
Yes, exactly.
Because the active toolchain is downloaded and cached in the local GeoPath PKG mod directory, it completely bypasses the need for sudo or administrator privileges.
And that is a critical advantage. In traditional setups, upgrading a system-wide compiler means you have to modify directories like user local bin or user lib.
Which means elevating privileges.
Right. You have to type sudo, which opens the door to inadvertently overwriting critical system libraries. Or worse, introducing malicious binaries at the root level.
Right, which you definitely do not want.
No. Go's self-contained user space caching means you can juggle 20 different compiler versions across 20 different projects, and you never once have to type a sudo password.
It confines the entire ecosystem to a sandbox that the user already controls. It solves version conflicts, root access permissions, and supply chain security all at once.
It's elegant.
It really is. And Ang actually specifically notes in the log how other ecosystems like Elixir and Erlang would deeply benefit from this architecture to resolve their own long-standing pain points with version managers.
This raises an important question regarding language design, though.
What's that?
Why haven't all modern languages adopted this self-managing statically linked architecture?
Oh, that's a good point. Why haven't they?
Well, Ang rightly observes that Go is uniquely positioned to execute this because of how it compiles. Go produces statically linked standalone binaries.
Meaning everything it needs is packed inside that one file.
Right. A Go compiler doesn't need a sprawling web of C dependencies, native implemented functions, or external linkers like GCC or Clang present on the host system just to run.
It is entirely self-sufficient. Contrast that with, say, Erlang or Node.js.
Exactly.
If you want to download a new Erlang environment on the fly, you often have to compile the Erlang virtual machine from source.
Which requires an intricate dance with the operating system's native C compilers and shared libraries.
Right. You are intrinsically tied to the host operating system's current state.
Yes. Go's simplicity at the binary level, the fact that the Go compiler itself is just a compiled Go program, is what enables this sophisticated bootstrapping.
It's turtles all the way down.
Basically, yeah. The language runtime can download a binary for the target architecture, verify its cryptographic signature, and execute it, completely ignoring whether the underlying Linux distribution is Ubuntu, Alpine, or Arch.
It isolates the development environment from the host environment entirely. So, tracing Ang's journey from start to finish, we really see this brilliant escalation of discovery.
We do.
It begins with the terminal aggressively returning Go 1.25.0 against an explicit absolute path to a 1.26 binary.
And that initial frustration forced Ang to look past the standard shell-level troubleshooting.
Yeah. Past the path variables and the shims.
And uncover that Go toolchain variable, revealing the dynamic routing capabilities of the host Go binary.
Which exposed the macro-level shift. The realization that Go is actively deprecating external version managers by turning its own compiler into a verifiable, self-managing modular dependency.
It's remarkable.
It reads the project blueprint, safely downloads the required tools into user space without root access, verifies them cryptographically, and executes the build.
It leads to a really profound architectural consideration, I think.
What's that?
Well, think about it. If modern programming languages are evolving to contain their own package managers, their own cryptographic verification logs, and their own dynamic execution routers,
Yeah.
completely walling themselves up from the host operating system's libraries and configurations, will our operating systems eventually become nothing more than passive hypervisors?
Oh.
Are they destined to just be dumb vessels whose only job is to provide network access and disk space for these brilliant, self-contained ecosystems?
The operating system simply becoming a bare, concrete foundation for these self-assembling factories to operate on. That is a fascinating evolution in system design.
It really makes you wonder what the OS of the future looks like.
It absolutely does. Well, thank you for joining us on this deep dive. The next time you find yourself fighting with a stubborn local environment or your system is explicitly denying a command you know to be true, take a step back and examine the underlying architecture.
You might be surprised by what you find.
Because, as Ang's log demonstrates, what looks like a maddening glitch might actually be a masterclass in engineering, silently working to keep your system stable. We will catch you next time.